Hello, and welcome to today's webinar, Solving Complex Thermal Challenges of Today's Space Market. I'm Amanda Hosey, your moderator for this 60-minute program, which focuses on technologies of current flight environments and future missions. Our speakers today are Brian Muzica and Tim Hahn of Advanced Cooling Technologies. Brian is the company's Vice President of Sales and Marketing and focuses on solving complex thermal challenges across multiple industries. He holds a bachelor's degree in mechanical engineering and an MBA and serves as a board member on the Keystone Space Collaborative. Tim is a product development engineer in the Orbital Space Group at ACT, where he has led and managed many programs in the space industry with rigorous design and production requirements. He holds a bachelor's and master's degree in mechanical engineering. If you have questions for our speakers, please send them through the Ask a Question box, and we'll address as many as possible at the end of the program. Also note, a PDF of today's slides may be downloaded under the Event Resources tab on your screen. Now on to the presentation. Welcome, Tim and Brian.
Thank you, Amanda, and thank you all for joining us today. We're really excited to present this webinar. We have a lot of content to cover today, so we'll jump right in, but I will say, just kind of as a prelude, this is a webinar meant to be a fairly high-level overview on several unique applications in the space industry. So while we'll touch on some of the technologies and use cases for those technologies, we don't dive into a lot of detail. So if you are working in those areas, please reach out to ACT afterwards. We'd be happy to go into much more technical detail on all the technology and use cases we're discussing here today. And just one slide on Advanced Cooling Technologies as a company. So we work in the spacecraft industry routinely. It's kind of at our core since our early days 20 years ago. But currently we're over 220 employees and over 200,000 square feet of office, lab space, and manufacturing. And we bring highly complex solutions to our customer base. So the space industry has been one of the areas where we've excelled using passive and active technologies, a lot of which are two-phase technologies, to solve some of the unique applications in space. So you can kind of see from some of the awards over the years that we have had a good amount of success in those areas. And just to provide some background, a lot of the use cases we'll talk about today stem from some unique applications, and we want to provide some level of detail of our experience in those areas. So ACT is currently on board over 35 satellites. So some of the more recent spacecraft satellite type programs that we've worked on that you probably heard about in the news are the DART program, Nancy Grace Roman Telescope, and Psyche, all of which have very useful missions for kind of humanity and the overall space exploration industry. And then some of the unique applications that we're going to touch on today involve cooling of lunar rovers. So ACT is one of the prime thermal companies for the Viper mission. So we're doing everything on there from the passive two-phase to the thermal control to some of the structural and radiator panels. So we've been kind of blessed with the relationship with NASA and long history for developing technologies for surviving Lunar Night, and that's where we'll go into detail on that program. Going to the bottom left, we are awarded a program with the Axiom team developing International Space Station. So currently we're in the development phase. I think we had a press release on this last year, but we're designing some of the thermal systems on that and looking forward to continuing working with them in supporting the thermal side. And then in the bottom middle, one of the areas we'll talk about today is lunar power generation, and ACT was one of the early companies focusing on high temperature heat pipes and other aspects that we'll go into detail more later, but the kilopower program was one of the primary drivers of a lot of the technology development that is being considered today. So for agenda, we're just going to go through some of the high-level thermal options. A lot of these, I'm guessing if you're attending this webinar, you're familiar with. But then we'll also talk about some of the more emerging technologies and then we'll talk about the application of those technologies for the unique programs we're talking about. So looking at a lunar rover program, space station, lunar power generation, and then just GEO or LEO satellites. So just looking at some of the spacecraft thermal solution options, and this is certainly a subset, but mainly the ideas we'll cover here today. So space copper water heat pipes, which are used prevalently in terrestrial applications, are starting to find a home in spacecraft for onboard processing and higher power FPGAs. Pulsating heat pipes is somewhat became more used in the industry or considered in the industry for heat spreading and unique geometries. Phase change material is a method to absorb energy, so that allows you to dampen cyclic heat loads or store for single-use type applications. Variable conductance heat pipes, we'll talk a couple different concepts around VCHPs, but that is a way to control temperature at the evaporator or at the heat source so that you don't need to rely on survival heater power, which can be very power consuming and a burden on the spacecraft. Constant conductance heat pipes, which are used very frequently in a lot of different applications, but on board many medium and high power satellites. So those are using ammonia to spread heat and transfer heat from source to radiators. Loop heat pipes, which is one of the most capable heat transfer technologies. It can move kilowatt level of heat very long distances and is a very capable technology. So we'll talk about that and some of the variants that we've been working on to drive down cost and lead time associated with that technology. And then we'll talk about liquid cooling. Typically, liquid cooling due to pumps and the failure modes has not been considered much in space applications, but as the need for higher power capacities is becoming more prevalent in the industry, liquid cooling is certainly finding a home. And we'll talk about variants of these technologies and some emerging technologies as we go through. And I think just before we get started into some of the applications, we did want to, for anyone who might not be familiar with the concept of a heat pipe, just bring a high-level technology overview of a heat pipe. So you saw heat pipe used a lot in the previous slide. There's a lot of variants of heat pipe, but at its core, a heat pipe is a passive two-phase heat transfer device. So it utilizes a pressure gradient inside, which is generated when you implement heat at any section along the heat pipe. It'll create a pressure and temperature gradient, which will boil the fluid at that area and push that fluid vapor to wherever it's colder in the system. Where it's colder or connected with a heat sink, it'll give up its latent heat, condense back to a liquid, and be absorbed in a wick structure that surrounds the inner diameter of a heat pipe, and that wick structure will passively pump the liquid back to the heated section. So this is a fairly simple version of a heat pipe, and as we've discussed, there's many different variants, and you can have multiple heat sources, but just to give an idea of what's going on internally, it's all driven on the principles of two-phase heat transfer. So with that, we'll take a look at our first application, so that being a lunar rover application. And in a lunar rover application, you have a lot of the same challenges you do in any space application, but a couple unique ones, and I guess the unique one is the ability to survive lunar night. So in most cases, if you're going to something like Viper, a polar region of the moon, you have to survive up to a 14-day period of temperatures below 100 K. So imagine having the need to survive 2 weeks at kind of liquid nitrogen temperatures. You have the need to control all your systems so that you don't overcool anything to the point of failure. So it's a big challenge in working with these applications to not only make sure you dissipate heat in nominal conditions, but you don't overcool or cause failure from the low temperatures in the period of lunar night. Another unique requirement compared to stagnant space programs like satellites is the ability to be mobile on a terrain. So these are going to be moving and going over hills and bumps, and everything needs to kind of work, and ability to have gyrations respectful of one another. So any thermal link that's coupling two surfaces needs to be somewhat shock and vibration tolerant, and those two surfaces may have relative motion according to each other. And the last point there is mass and power budget. So with these, there are, to get it to space and to operate in space, there's limited volume and mass capable of putting in. So you need to be very cognizant of your overall thermal system and make sure that it doesn't consume power. So most of the technologies we'll talk about are passive, and it's also very mass optimized so that you can operate and transition the rover from different sites and launch it into space. So with that, we'll talk about a couple technologies. The first being loop heat pipes. So many of you probably know loop heat pipes from their place in satellite programs. So just to give somewhat of an overview, a loop heat pipe is a very high-performing variant of a heat pipe. It utilizes an evaporator body, which is a very unique constructed device, which creates such a high pressure gradient that you can push fluid vapor very long distances. So this allows you to move extreme amounts of heat. A single loop heat pipe can carry over 1 kilowatt of heat. It also allows you to move it very long distances. So the pumping capability of an evaporator body has been proven greater than 60 inches against gravity. So it also allows for ground testability. But one of the main reasons to utilize it in a rover application is because of the flexible links that allows. So because all the technology and two-phase operation is going on in the evaporator body, the condenser is mainly tubing. So it allows you to route that tubing in such a way that it can provide flexibility in your system. And again, with that operation of the rover moving over terrain and the radiator panels moving at a different frequency than the heat source, that can eat up a lot of that vibration and control. So a loop heat pipe is somewhat of an ideal application for those reasons. And another technology being utilized, and again, this is one of the drivers in the requirement to survive lunar night, is a passive thermal control valve. So in this technology, we're utilizing a non-condensable gas, which is placed over cavities in the bellows, and it allows you to passively, so no power required, create an on-off switch. And so this is typically coupled with a loop heat pipe near the warm box, which is an electronics box kind of centered in the center of the rover that can't be overcooled. So when you go into that period of lunar night, you don't want to overcool the warm box. So this allows you to basically decouple that thermal link from your source to your sink so that you don't get additional heat transfer. And you can see from some of the figures here, there's a couple different modes of operation. So it can be designed in a couple different ways based on the design requirements. But the big key here, and what we've been working with NASA to provide, is a control valve that operates passively, but is also smaller in volume and lower in mass than what's typically provided in industry. So we've done a lot of work with this, being supported by NASA, and are in a point now where we feel confident in the design capabilities here. And the next technology we'll talk about is phase change material. So this is a way to absorb thermal energy through phase transition. We talked a lot about liquid to vapor phase transition. This one is solid to liquid. And during that solid to liquid phase transition, you can absorb a significant amount of energy by the latent heat diffusion of a material. So these are typically paraffin wax or some other materials that have high latent heat diffusion. And as you go as you go during that melt period, you can absorb energy. So what you're seeing in the top right figure is kind of an example of what a solid component would give you in terms of the red line, which is the more or less specific heat line, and then what a phase change material will get you, which is the blue line. So you follow the specific heat curve up to a point of melting, and then you basically level out and can control temperature or absorb energy without increasing temperature during that melt zone. And then once you're fully liquid, you would again operate on the specific heat curve. But utilizing this in the case of a rover gives you some options to absorb heat loads instead of having a more complex system. So if you do have cyclic heat loads, you can absorb that energy and then design your downstream cooling system, like your radiator panels, for average heat load as opposed to peak heat load. So that gives you some flexibility in your design. And I think those are the key technologies we want to talk to about rovers, so I'll pass it on to Tim to talk about space stations.
Yeah, thanks, Brian. So this is Tim Hahn. I'm a product development engineer in the Orbital Systems group. So I'm going to talk about some technologies that are being used in space stations with regards to the thermal control. So so the main thing with space stations is they are large and complex. So as a large spacecraft with more thermal needs, that's when you start considering active systems with pumped liquid to remove as much heat as needed from these large systems. With liquid cooling loops, then we start talking, you're going to need cold plates and then accumulators to take care of your expansion. There's also some needs then on space stations for VCHPs. Those are variable conductance heat pipes Brian touched on before. We'll go in a little more detail there. And then we're not going to get into too much, but we're also developing some components for actual air conditioning systems on the space stations. When we're talking about liquid cooling, this can be used for long distance travel. We're cooling an entire space station with a long liquid loop. We can take a lot of power out from this, and it can be done with single or two-phase loops. So a single phase, we're just pumping liquid through, takes out a lot of heat. But additionally, a two-phase system will allow for evaporation to occur, and that can remove even more heat with some added complexity. So in these large systems, with temperature changes, everything will expand and contract with that temperature. So accumulators are what we need to use to keep the pressure consistent, or we can vary pressure as well with a more active accumulator. So there's two main types of the accumulators. So the single and two-phase choices here. For single phase, typically are a bellows type where it's there's a spring holding a constant pressure, and then bellows to account for changes in volume. The two-phase gets a little more complex. Typically, we still want only liquid to be in, to be coming in and out of the accumulator, but within the reservoir, we can have two phases there, and we can heat the liquid inside to boil it off and increase pressure. And so, by using sensors, heaters, possibly even radiators directly on them, we can control the temperature of the accumulator. And by controlling temperature, we're controlling pressure in the system. And then your entire loop can be controlled by that one accumulator as far as pressure goes. And so in addition to that, we have a few different cold plate technologies that we've worked on. So aluminum vacuum brazed is a good choice for certain applications. So the cold plates are are how you're going to get your liquid loop to connect to your electronics or whatever your system that you need to connect to. And so aluminum vacuum brazed is a pretty typical use. We've also done some stainless steel vacuum brazed, which can improve weldability to other parts of the system. There's the tube and plate style that's been pretty common, and then CCHP style is a very interesting type. For the CCHP style, it's not a CCHP, but we're leveraging the CCHP geometries that make lightweight plates that are really just tubes with flanges on them instead of a solid plate. So that's just a method to get a more lightweight plate where we can either serpentine the tubes, we can have manifolds and parallel paths. So depending on the need, we can change geometry around quite a few ways. So variable conductance heat pipes, touched on a couple times here, or VCHPs. The main part of a VCHP is to save you battery power when it gets cold. So VCHP varies the conductance by increasing and decreasing the condenser length. So if you picture a constant conductance heat pipe as this heat pipe here, but without the gas reservoir, the one challenge of CCHP production historically has always been to remove all NCGs or non-condensable gases from the system, because NCGs are always considered bad in a CCHP. You don't want NCGs. But for a VCHP, we can actually introduce them intentionally, and really what we're doing is making the heat pipe less effective when it gets cold. Because typically, if you want to keep your electronics at, let's say, 20 degrees, you want them to be cooling as much as possible when it's over 20 degrees, and you want it to not be cooling when it's under 20 degrees. So we can set that point wherever needed, but the benefit here is that when it gets very cold, these heat pipes don't work very well, and that will save you heater power on the evaporator side. And we know batteries will eat up your mass budget pretty quickly. So overall, it's a big savings. We can also, by putting sensors, heaters, and potentially its own radiator directly on the reservoir, we can control that temperature. And by controlling that temperature, we can also vary the conductance actively. So with a little extra complexity, we can get even better control.
Excellent. So now we've put an unmanned vehicle on the moon and have done experiments and sent people to the International Space Station. So now we're going to look at fully inhabiting the moon with humans. And to do that, one of the big keys in solving that problem is generating power to sustain life. So in this section, we'll kind of talk about some of the thermal challenges that go along with high-level power generation on the lunar surface. So in many cases, there's a lot of options, but for space, there's really not too many applicable options that could make their way up there and generate a significant enough level of power. So The two that have been mainly identified have been solar power, which is used frequently on things like satellites and rovers and such, but that's a challenge to generate a significant amount of heat load, or a significant amount of power. And probably the most useful technology to develop enough power and energy long term is nuclear. So in those areas, it's something that NASA has been considering for decades and has been providing a lot of funding in terms of SBIR and civil funding for companies to continue to develop this and leverage the terrestrial development side. But it does come with a lot of unique thermal challenges. So the temperature ranges, the safety considerations, the transport, a lot of unique challenges when you're dealing with nuclear systems, and that's a lot of which we'll get into today. So again, just to kind of go through some of those, the big one is to safely remove heat from the core. So that temperature range is greater than 850 degrees Kelvin, and you need to move that heat and transfer it fairly long distances because you need to couple it with enough radiator surface area to fully dissipate the heat load. So it's a fairly challenging and robust problem from that standpoint. And in terms of getting it from or rejecting it from the cold end, again, because of the scale of the heat loss, you need to have a fairly economical and scalable solution on the cold end side. So looking at a couple different technologies on the hot side, this is leveraging a lot of our work that we've done for kilopower, but we also generate these high temperature heat pipes for a lot of terrestrial use as well. We have a pretty routine line called isothermal furnace liners that use these in calibration equipment across national labs across kind of the globe. But at its core, it's a heat pipe, but it uses liquid metal as the working fluid and superalloys or stainless steel as the envelope material. So in most cases, it is coupled with the core, and then it takes heat out from the core and then takes heat to the brain cycle and Stirling engine. And looking at this slide, you can see some of the fluid options. So typically, potassium, NaC, or sodium are good fits for these applications. And then getting the heat out from the hot end is one area, but there's also the cold side challenge as well. So in this, you're taking heat away from the power conversion device, and that temperature range is typically in the 300 to 350 C range. And to do that, a lot of times you're using some type of fluid loop, but you also need to collect the heat and pass it to a large amount of radiator surface area. So in many cases, we're looking at heat pipes as a passive way to collect heat and transport it to those radiator panels. And because of the higher temperature range here, ammonia or traditional working fluids in the space industry are not as ideal. So we're looking at options such as titanium water heat pipes to kind of fulfill this operation. And then a lot of the work we've been doing is developing solutions where the construction can be scalable and economical. So that's what you're seeing on this figure. The bottom right is some of the earlier stage heat pipes and radiator panels, and then the top is more of the more recent developments where we're using annular evaporators around liquid lines to take heat and then run it through a heat pipe passively to the radiator panels. And that, again, is a pretty scalable technology where you can add heat pipes and radiators based on the power level of the nuclear source. And we did want to, since we'll send this slide package out to those on the webinar, we did want to provide some more detail on these areas. So we have published a fair amount on these subjects. So We will provide the slide package, and it does have links to these papers. So please feel free to look at those. And again, we're just kind of scratching the surface on today's webinar, but if you are interested in more detail, if you're working in the space, please be in touch with us, and we'd be happy to go into more detail and bring in our subject experts.
All right, thanks, Brian. So this is Tim again. So I have a few topics here about thermal controls on satellites. So typical challenges on satellites, they are not the size of the space station. We're talking about low to medium power, but the one big concern is always mass, of course, and then keeping sensitive electronics in an acceptable temperature range. So there's a few technologies that we have developed that help keep the temperatures in an acceptable range while not increasing the mass more than necessary. So as Brian touched on before, copper water heat pipes are great for electronics. The temperature range for electronics are typically perfect for water. Water has a high latent heat. So really everything about copper water heat pipes are great for cooling electronics. The one problem in space is that sometimes it's hard to keep them above 0 degrees. So when water freezes at 0 degrees, it expands, which is very unfortunate. This has historically been the reason that copper water heat pipes are not used in space applications. So if you can keep everything above 0 degrees, that's great. But if not, it becomes an issue of how many cycles will the heat pipe last. So what we've done at ACT is developed manufacturing methods and different designs to increase the robustness, increase the number of cycles that copper water heat pipes can take. And by cycles, I mean freeze-thaw cycles. So this table here is really helpful for seeing the differences. So ammonia freezes at a much lower temperature, at -77. So those can be used for lower temperature applications, whereas the space copper water has benefits in heat flux and often size too. They can be made smaller. So they both have their place. Really, the space copper water heat pipes are ideal at a box level, so on individual boards or within individual electronics boxes is where space copper water heat pipes are ideal. And then for longer ranges, that's where the VCHPs, the aluminum ammonia, are still going to be better. So one way to get around the freezing then is the development of pulsating heat pipes. So with pulsating heat pipes, we can do smaller geometry. We can have a heat pipe on this board level, but we can actually use ammonia, propylene, refrigerants, other working fluids that don't freeze where water freezes. So that's one benefit of the pulsating heat pipe. The way these work is slightly different. So instead of, if you remember the diagram before where a standard heat pipe, copper water, it will evaporate on the evaporator side and will go through the center of the tube. The way the pulsating heat pipe works is at the hot side, wherever that may be, it will start boiling off, and because there's no direct way to go here in this loop, in this channel, it uses the instability of pressures to make the liquid within this channel pulsate back and forth. And those pulsations will absorb the heat at the hot side, and then they will remove the heat on the cold side. And the pulsating back and forth will act the same way as a heat pipe, even though it works pretty differently. So the pictures on the bottom here, the left two are the same part, but you can see how detailed the geometry can get with a pulsating heat pipe. It doesn't have the limitations that the space copper water does in size. You can get very small features. You can get very tight bends, like the picture on the right. We have a pulsating heat pipe along that bend. It goes on both the bottom and the right side there. So very small features, tight bends, complex geometry. Those are all the benefits of pulsating heat pipes. So another common thing on satellites for temperature control are CCHP panels. So if you've worked with aluminum honeycomb panels before, you know they are lightweight. They're good structurally for how light they are, but they do have very poor thermal conductivity. It's hard to get heat to spread on the radiator panel or on the structural mounting panel. So by embedding CCHPs in these honeycomb panels, you can get the thermal spreading that you need in that lightweight structure. So at ACT, we've developed a lot of design tools and calculators to make an optimal layout for a panel. So a typical satellite might have a structural panel where your electronics are mounted, and that needs heat pipes embedded to remove the heat from the electronics boxes and take them out to the sides of the panel. And then you might also have radiators that have a heat input, but that heat needs to be spread around the radiator. So we can embed CCHPs into that panel as well. Another technology that we've developed here goes back to the loop heat pipe that Brian talked about before. And the difference here is that the evaporator body of the 3D printed loop heat pipe is a single 3D printed part. So using additive manufacturing, we can combine multiple parts into one, and we can solve the problem of the complexity of the standard loop heat pipe evaporator body. So a typical loop heat pipe will have a tightly packed powder wick, and that has to get embedded into an evaporator body, and that's a tough problem to solve in manufacturing, and it can be very expensive. So 3D printed loop heat pipes can decrease costs a good bit, up to 75%, and can also be a lot faster because once it's printed, it's done, it's ready to go. So up to 50% schedule reduction. And then the main drawback with today's technology in 3D printing is the pore size. We can't get quite as small of a pore in a 3D printed structure as we can with a powder structure. So that limits the amount of heat transport. So we've demonstrated over 450 watts of transport, and that's compared to the over 1,000 watts transport from a standard loop heat pipe. So we're very excited about this technology improving and making loop heat pipes more accessible. And with that, I'll go back to Brian.
Yeah, maybe just one more note on the 3D printed loop heat pipe. If there are interest and have use cases, we're really excited about this technology, have been developing it, and we currently have an open opportunity for a sequential phase 2. So we are looking for companies to support that with strong use cases. So if you're interested and have that kind of need for a deployable thermal link that might not have the funding to do a full loop heat pipe, but you need something more robust than straps or other options, it's a really good technology, and we'd love to work with you.
I think important is we reach 2 micron pore radius, but the permeability is still behind.
So if you didn't hear that, we've reached 2 micron pore size, but the permeability is still behind. So that's what we're working on.
But the permeability is still to catch up.
Okay. With that, as you could hear, we're lucky to be joined today by Colleen Tarou, who is one of our principal engineers on a lot of these programs. But the reason we brought him in was to introduce the thermomodulating heat pipe concept. So this is something that ACT has been co-developing with AFRL, and we're at a really good point right now where we're looking to start bringing it out to the industry. We've done a lot of the unique work to kind of prove out some of the design considerations, but the concept was somewhat developed by AFRL to bring a lower cost option of a variable conductance heat pipe to the market and provide some unique capabilities to serve as both a traditional variable conductance heat pipe, but also a diode heat pipe. So with that, I will pass it on to Colleen, who's been working on this for several months to a year and is really the technical expert on this.
Thank you, Brian. You said almost everything from introduction point of view. Hi, I'm Colleen Tarou, and as Brian said, I'm a principal engineer in research and development at ACT, and I'm going to give a few details, just a few, because the time is very limited, and the questions and answers we're already eating this time, into this time. So thermomodulating heat pipe, AFRL came up with the concept and funded ACT to develop it, to assess contributions to thermal control and also limitations, and in the end to identify applications and to market on the market for it. So what is a thermomodulating heat pipe? A thermomodulating heat pipe looks, and it is a CCHP. It's a constant conductance heat pipe that has a non-condensable gas charge, just like a VCHP. Well, they look the same, CCHP and thermomodulating heat pipe. The difference is a non-condensable gas amount, controlled on purpose. Now, a thermomodulating heat pipe combines, as the slide says, a VCHP behavior with a thermal diode behavior. The main function a thermomodulating heat pipe will serve into a system as a thermal control device is the diode effect. The VCHP effect, in other words, the direct mode of operation, is kind of a bonus. It's loose. It's not because the reservoir is small, and but it's still useful. A thermomodulating heat pipe is a thermal control device that allows the usage of more than 2 radiators on a spacecraft because it protects the electronics from sun exposure, so the radiators would not dump heat into the electronics, the parasitic heat. Thermomodulating heat pipes, through their diode effect, would mitigate, stop heat going into undesired places and situations. For a better understanding of the concept geometry view, I'm showing on the right-hand side of a diagram, a cartoon of the specific sections of the thermomodulating heat pipe. It does have an evaporator and a condenser. The smaller one is the evaporator, the larger one is the condenser. However, we pay the price by having non-condensable gas inside by reducing some of the conductance in the direct mode of operation. So the first from those three images shows a relatively well open condenser for direct heat transfer as needed. Now, if the sink temperature goes down, more heat is tended to be sucked out from the evaporator. Then the front, generated by the non-condensable gas, advances upstream, blocking more of the condenser. In other words, increasing thermal resistance and minimizing the fluctuation of the sink of the heat source, which is the evaporator. Now, if by some reason now we go to the third one, but if by some reason temperature gradient of the pipe reverses, so for example, the sun hits the radiator, then the radiator heats up, and even more than the heat source, even more than the heat source is allowed to, then the non-condensable gas is swept by the vapor flow and changes the location entirely into the pipe and blankets the evaporator, impeding entirely or almost entirely by design the heat access to the evaporator. So this is the thermomodulating heat pipe. The way it looks is on the left or the lower portion of this slide. Now I'm going to the next slide, and I will spend probably even less than on this. I'm showing just some testing results for better understanding. The top two pipes are VCHP mode. The bottom two heat pipes show a diode mode of operation of the same heat pipe, obviously. The testing results, first we tested in VCHP mode, which are the black dots on the red on the right. The red dots are in the diode mode. Conductance is shown on the abscissa, and the radiator temperature on the abscissa is the radiator temperature, on the ordinate axis is the conductance. As you see, now let's take a look on the front, on the upper left. For a colder temperature, for example, I go to, is my point, my prompter, is that? If we go to, from the left to the right, the second data point, where the arrow starts from, we have a sink temperature of approximately minus 65. We see the condenser opened of a certain amount. If we go to the right, to the fourth data point, let's say to the minus 25, we see the condenser open more. So the payload increases in temperature slightly and compresses the non-condensable gas towards the end of the condenser. Or the other way, the sink temperature increases and generates this pressure increase, but because the vapor pressure increases faster than the non-condensable gas, according to the ideal gas law, front goes more to the right and opens more of the condenser. So then payload temperature fluctuation is less than the sink temperature. So now when you go on the bottom, we reverse the gradient. So for a certain radiator panel, let's say the first point at 55 degrees C, the front, this is the temperature of the radiator. Of course, the non-condensable gas reverse is at the left, and the front is somewhere in the adiabatic section. Obviously, vapor does not have access to the evaporator. If we go higher in evaporator temperature, in the radiator temperature, the front is pushed more to the left because vapor pressure obviously increases, and we know increases fast. We are already on a very ascending, very steep vapor pressure portion. So the conductance increases. When I say conductance, it's parasitic conductance. So on the right, now we go to the plot with black. We see desired conductance, direct mode of operation conductance. With the red on the bottom, we see parasitic conductance. We want to see the red one as close to zero as possible. So these are preliminary tests. We are within the process of developing this device, and hopefully in the number of months from now, we'll be able to present more and more applications and context of usage of this device. Thank you.
Okay, with that, we'll move into a Q&A session.
Yes, thank you very much, Brian, Tim, and Colleen for that interesting presentation. And just a reminder to the audience, you can still submit questions for the speakers through the Ask a Question box on your screen. Now, we have a lot of questions that have already come in, so we can get started. First up, someone asks, these seem like fracture critical components. How robust is the design to mitigate ammonia gas leakage?
Sure. Yeah, so I can handle that. Yeah, when we're talking about ammonia, we're at its most basic, we're talking about CCHPs. So we can use CCHPs as an example here. So the way these are typically assessed for risk, we do consider them a pressure vessel. It is a potential risk to have any ammonia charged heat pipe of any sort, and so from externally to the heat pipe, you would not want to have anything putting it under external stress that would cause it to rupture. But internally, as a pressure vessel, the short answer is analysis and testing. Each CCHP goes through a number of analysis and testing. So every single heat pipe will have pressure testing in the form of pressurized gas introduced, and then also after it is fully manufactured and sealed, high temperature test, which increases the pressure. And so through analysis and testing, they are proven to be robust. And then the real limitation then at the end is a temperature limit to not exceed that temperature for safety reasons. And then the mark really is the number of hours on orbit. Brian, what is it?
Over 70 million.
So over 70 million hours on orbit combined of all of our CCHPs with 0 failures. So that's that's how we address that.
Great, wonderful. Thanks, Tim. Next up, someone asks, can ACT help me even if I'm not looking to build any hardware yet, but want to see where my heat loads are and how I can use system level cooling to distribute the heat?
Sure, yeah, absolutely. So today's webinar did focus a lot on the technology and hardware side, but yes, we have full analytical capabilities in-house. So we'd be happy to help you. We have multiple component and system level research and product development engineers that have a lot of experience, and we also have seats of thermal desktop and system level thermal analysts to look at different orbital profiles and thermal profiles associated with different missions. So yeah, absolutely. If there's a challenge from some of our viewers on the analytical side, we could certainly support that.
All right, great. Thanks so much, Brian. Next up, can I use constant conductance heat pipes and space copper water heat pipes together?
Sure, yeah, a good question. So you certainly can. They do have good kind of use cases together. So what Tim presented earlier was where copper water heat pipes are used a lot at the device level to spread out the high heat flux component, move it to either the chassis or where it would get picked up by a CCHP in the system level to take it to a radiator panel. But there are a lot of use cases where you can couple those technologies and move it closer together. ACT actually has a patent on integrating copper water heat pipes within a aluminum ammonia CCHP flange so that you get the heat flux and spreading capability of the copper water heat pipe before the heat enters the vapor space of the ammonia, so that you lower the heat flux before it hits ammonia and then can take it longer distances. So yeah, good question, and certainly we are looking at ways to kind of use those technologies in conjunction and combined to help the overall spacecraft architecture.
All right, great. Thanks, Brian. Next up, a two-part question. First, can loop heat pipes act as variable conductance devices when the heat load is low? And second, is there ability to shut off similar to VCHPs, or do they not shut off?
So loop heat pipes for thermal control, typically they use heat, so they are not passive. They're active. So yes, the answer is yes. It can be shut down. Can be having a set point control by maintaining a certain temperature of the composition chamber. And the other question was?
Sorry about that. The other part of the question was, is there ability to, sorry, you answered that word. Can loop heat pipes act as variable conductance devices when the heat load is low?
Yeah, when the heat load is low, yes, in the same manner. It depends how low, because the loop heat pipe needs a minimum power to operate to maintain the temperature gradient between evaporator and composition chamber. Now, it depends. If you are below that minimum power, it's hard to answer.
It's not exactly variable, but there is a startup power requirement.
No, but it was about VCHP, thermal control.
Yeah, I think it's fine.
So the answer is yes. Applying, still manipulating, playing with the condensation chamber temperature.
Yeah, I think if the person who wrote that question has a specific use case that they're thinking about when they wrote it, please email us. We'd be happy to dive more detail into that.
All right, great. Thank you all for that. Let's see. Why would you consider space copper or water heat pipes over pulsating heat pipes and vice versa?
Yeah, that's a good question that I think is being asked a lot in the industry. So I guess just going to some of the things Tim presented on, space or water in general is a very capable working fluid. So when you're connecting space copper water heat pipes at the device level, you can handle that high heat flux, and it's also an ideal working fluid for the temperature ranges in which electronics want to operate. So in kind of a single point-to-point, space copper water heat pipes is likely to be the ideal solution. The challenges come in from a practical standpoint. When you have unique geometries, like Tim alluded to, you might have very thin profiles, or it might need to go around very tight bend radii, where pulsating heat pipes, because of their construction and no wick structure, can do that. The other big use case that Tim talked about is the freezing of water. So if you have operation, which most spacecraft will see some temperatures below zero at certain points, if you have operation there, you'd like to characterize that as best you can. So the work we've done with space copper water heat pipes to date has gotten them to a very robust freeze-tolerant state, but that's still only hundreds of cycles. So if you're getting into a LEO operation when you might see thousands of freeze-thaw cycles, that's where you might want to go to a different working fluid. And when you go to a different working fluid, the operation of a pulsating heat pipe is much more ideal than a constant conductance heat pipe, because you can get that localized spreading, handle pretty high powers, and have all those other benefits that Tim mentioned earlier.
All right, thanks so much, Brian. Unfortunately, that's all the time we have for today. I'd like to thank Tim Hahn, Brian Musica, and Colleen Tarot for sharing their expertise, and thank you to our audience for joining us and for all of those wonderful questions. I know there were many we didn't get to, but note we will supply the speakers with any that we didn't answer live so that they may follow up later. As a reminder, you may download a PDF of today's slides under the Event Resources tab on your screen. In just a moment, a survey will pop up. Please tell us what you thought of this program by answering 3 questions. And this webinar will be available on demand for the next year, and an email will be sent to everyone who registered as soon as the archive is ready. Once again, thank you all for watching.